Good morning, everyone, and happy Earth Day. Hopefully you are thinking of new ways that you can take positive actions to celebrate today and every day as Earth Day. We have been, at my house, been doing a few cleanups around our neighborhood, picking up litter and those kind of things. So think about what you can do to either save water, protect our natural resources around us. Today we have a really fabulous presentation from Lainey Meredith. But before she starts, I wanted to give a little bit of housekeeping, general information about the webinar format. By now, everybody's probably old hat at participating in webinars, but just so you know, you will be on mute throughout this presentation. We do really hope we get a lot of questions, and we'll take time at the end of the presentation to get to those questions. And if we don't have time during our period of time for this presentation, so before noon, I will make sure that we get back to you in writing with the answer to those questions, because we do want to make sure that any of your questions that you have do get answered. So that is how those questions will be taken care of. We have also wanting to make sure you know about our next webinar. It will be May 6th, and it will be a presentation about the Springs projects in the St. Johns River Water Management District, and that will be given by Melissa Dialoso. And so if you're interested in some of those, then we hope that you'll tune in for our next webinar. So without further ado, I would like to introduce Lainey, one of our hydrologist fours in the Bureau of Watershed Modeling. And I know that there's a whole lot more that goes along with that. So it's the Bureau of, I can't get to the Bureau of Watershed Management and Modeling. And so Lainey has a master's and a bachelor's degree from the University of Florida and has been at the district for a little over 5 years, or right around 5 years. So Lainey, I'll hand it off to you.
Thanks, Jennifer, and thanks for giving me the opportunity to present today on groundwater modeling at the St. Johns River Water Management District. So today I hope to give you some information about what groundwater models are, why we make groundwater models, and how we use them here at the St. Johns River Water Management District. Okay, so before we get into modeling, I'm going to cover just some groundwater basics about groundwater flow, give you guys some definitions that'll kind of help you better understand when we get to the modeling part. I'll go over a high-level overview of Florida geology. Then we'll get into the nitty-gritty of modeling. I'll go over some model applications of how we apply these groundwater flow models here at the district. I'll give you guys some examples of groundwater flow models that we use. And like Jennifer said, we should have some time at the end to take some questions. Okay, so groundwater, it exists underground in the void spaces found in soils and rocks. So these underground materials that are porous and that can store and transmit water, we refer to those as aquifers. So in Florida, as we all know, groundwater is a very important resource. It's our primary source of fresh water supply in Florida. Over 90% of the people in Northeast and East Central Florida get their drinking water supply from our underground aquifers. And Florida's aquifers are some of the most productive in the world. So we have a lot of storage underground, like you can see in this picture. Due to Florida's unique geology, we have large quantities of water that can be stored underground. I'll get into some of the details of this in the coming slides. However, as we all know, groundwater usage has a limit, and so I hope through the rest of this presentation, you'll get a little bit more background about how we use groundwater flow models to understand our water availability going into the future. So most of the water that is available for recharge to our groundwater flow system comes from rainfall. So in Florida, rainfall is a huge part of our water budget. We get on average about 50 inches per year of rain. However, not all of that rainfall makes its way to what we call the water table, shown by this surface here. Some of that rainwater is evaporated away at the surface or transpired. We combine those terms into what we call evapotranspiration here. So like these arrows are showing, these are processes that are removing water that would be available to recharge our groundwater flow system. We also have irrigation that's applied at the surface. Some of this water can also make its way through what we call this unsaturated zone and actually hit the top of the water table and become recharged. Some of that water can also run off into our surface water bodies, so our streams, our rivers, and lakes. Um, Surface water and groundwater do interact with each other, and that's an important part of groundwater modeling as well as surface water modeling, is understanding that interaction. So you can have surface water exchange to the surrounding aquifers, you can have loss happening and seepage, or you can also have groundwater that is directly flowing into our surface waters through base flow or springs. Um, so like you can see here, I just wanted to point out that at this water table surface, below this zone, we have complete saturation. So all the void spaces I mentioned before, those are fully saturated with water. So rocks underground have different characteristics that control groundwater flow. So these are porosity and permeability. So if you think of the aquifer as a sponge, shown here in this example, this part of the sponge has all these holes in it, right, our spongy texture. You can think of that like the porosity of a material. So that's the total volume that can be of storage in that material that water can be stored in. Along with porosity, there's another term we use called permeability. So while porosity relates to how much water a material can hold, permeability relates to how that water moves through the material. So more so the connectedness of the different void spaces controls permeability. So different rocks have higher permeability than others, and they act as aquifers. These would be things like sandstone or limestone. There's other rocks or materials like clay, for example, that act as barriers to flow. So these are materials that have a really low permeability, and they behave as what we call confining units in our groundwater flow system. So if you look at this illustration over here, this is just an illustration of an example aquifer system. So we have our different confining units, this lighter beige color, and then we have our aquifers, which are the gray color here. If we have a confining unit above an aquifer, we call that aquifer confined, and so that aquifer is under pressure. Groundwater flows differently in confined and in aquifers versus confining units. So if you look at these blue arrows here, they're illustrating groundwater flow paths. So when water is recharged at the surface, like we previously talked about, water will always flow from higher points to lower points. So we call this hydraulic head. Put generally, hydraulic head is the elevation that water would rise to in a well. So if you look at these flow paths, from when the water is recharged, you can follow one of these and see that it's flowing towards the lowest point in the water table, which in this case is a stream. So if you think of this like the St. Johns River, this could be groundwater that's actively flowing into the river through base flow. Okay, so just a very general overview of Florida geology. We could probably spend a whole webinar on just Florida geology, but for the purposes of groundwater modeling, I wanted to just introduce the major aquifer systems in Florida, the ones that we're primarily modeling groundwater flow in with our groundwater flow models. So at the surface, our shallowest aquifer systems are generally defined as the superficial aquifer system. These can consist of different materials depending on where you are in the state. It's mostly made up of sands. And this aquifer is unconfined, so we don't have a confining unit on top of this aquifer. If you look at the picture over here, this shows you the location of these major superficial aquifers in the state of Florida. In parts of South Florida, they have a limestone aquifer here called the Biscayne Aquifer. And in Northwest Florida, they have a productive superficial aquifer over here. The intermediate aquifer system is a localized aquifer system, so it's not as important in our district, but in Southwest Florida here you can see there's a zone of productivity here. This aquifer system is thinner, it's confined, so it's made up of different layers of sand and limestone that are actually separated by clay units. And then getting to our main major aquifer system, this is where we get most of our drinking water supply. This is the Floridan aquifer system. So this is a sequence of really thick rocks. These are carbonate rocks. When I say carbonate, we're talking about rocks that were deposited millions of years ago when Florida was covered by shallow seas. So I'm mostly talking about limestone here. There's also dolomite is another rock that's a carbonate rock that we have in our aquifer system here. The Floridan aquifer system is regionally extensive, so you can see the extent of the aquifer system in this lower map. It extends not just through Florida, but also through Georgia, parts of Alabama, and South Carolina as well. And it's separated into what we call an upper zone and a lower zone that are separated by a middle confining unit. Like I said, the aquifer system is very thick. On average, it's about 1,000 feet thick. So just to give you a scale of the size of these rocks underground that are behaving as aquifers. So there are parts of the state where the Floridan aquifer system is unconfined or very thinly confined. So in our part of the district over here, you can see that the upper Floridan aquifer, indicated by the brown colors, is pretty heavily confined. So we have a thick set of mostly clay on top of the upper Floridan aquifer that's confining that aquifer. There are places where it's starts to thin, and so we have thin confinement in this lighter brown color. And then there's areas indicated by this bluish color here where it's unconfined, meaning that the limestone is actually very near or at land surface. And the reason this happens is because carbonate rocks like limestone are soluble. So over long periods of time, groundwater circulating through the rocks can actually dissolve and erode away at the rocks. And because of that, we get very unique features here in Florida, such as karst springs. So we have a lot of springs in Florida. There's actually over 700 springs in Florida. Close to 150 of those are in the St. Johns River Water Management District. Some of my favorite springs, I purposely put these in here because I love visiting these springs. So Blue Spring in Volusia County, Silver Springs, Silver Glen Springs. If you haven't been to these springs, I highly recommend going and taking a visit. But these springs are illustrations of places where groundwater is discharging at the surface. So we have an interaction here between the geology and groundwater that's contributing to these formations of springs. Um, Also, mostly in the area I showed you in the previous map where the aquifer is unconfined, we can have some negative consequences. So in those cases, you can actually get sinkholes that develop, kind of what I'm showing you here in this lower picture. So sinkholes occur where there's a breach in the confining unit, and so you actually have collapse that can happen at the surface. Part of why that collapse is happening is because underground we have the development of, large caverns, conduits, and openings in the limestone due to that process over time of groundwater circulating through and just slowly removing that material. Okay, so I kind of went through groundwater basics in the previous slides, and now we're gonna switch gears and go into modeling. So I know when people hear the word model, they kind of get a little scared. It can get very technical, but I hope that I've kept this simple enough that I think you guys will come away with a better understanding of what groundwater models are and why we use them here at the district. So what is a groundwater model? To put it simply, it's a simplification of our reality. So a model is a mathematical representation. In this case, we're representing the groundwater flow through an aquifer. So there's a series of equations that we use. I purposely didn't put in any differential equations in this PowerPoint, so you're welcome. But there's a set of governing equations that control groundwater flow, and our model is using those equations to simulate flow and calculate hydraulic head. There's different ways to solve groundwater models. Throughout the rest of this presentation, I'm going to be focusing on numerical groundwater models. What I mean by that is the numerical models usually use a computer code for solving groundwater flow. And so these numerical models, they're more complex, but they also allow us to capture the heterogeneity we have in our system rather than other approaches that we have to make assumptions, like uniform assumptions about our system in. So when I talk about a computer code, I'm almost always referring to ModFlow. So ModFlow is a widely used computer code developed by the USGS. It's used by us and by multiple agencies and water management districts for solving groundwater flow models numerically. So if you want more information about that, you can go to the USGS website and you can download the software from there, and they have lots of documentation on ModFlow. So groundwater models can be what we call steady state or transient. So steady state models, we're making an assumption of an equilibrium condition. So we're making the assumption that there's no change to the system through time. Transient models, conversely, are time dependent. So we're simulating the response to stresses in our groundwater flow system through time. So now to the question of why do we model? It seems complicated, right? Why do we do this? So models are essential for understanding our past, our present, and using that understanding to predict consequences in the future. So we need these models to make informed analyses about our system and understand consequences of changes to that system. So there's many other uses of models and groundwater models specifically. They allow us to integrate all of our field data. So we have a very extensive hydrologic data collection system here at the district, as well as other agencies have similar data collection efforts. And models allow us to kind of integrate all that data into a single framework. They allow us to test ideas about how the system behaves, but they can also be useful as screening tools. So we may, through our modeling process, we may learn that we actually feel that we need more data in a specific area to help us understand what's going on there. And so it can be useful in that respect as well, for informing us about the system. And models can be used to estimate properties or flows where we just don't have data available. So, a limitation obviously is we don't have data everywhere. It's limited in where we do have data, and we often have to make assumptions or interpolations between where data does exist. So models allow us to do that. And then, like I mentioned before, they can be used to simulate responses or changes under hypothetical conditions. So, as the population increases in Florida, we're going to have more demand for groundwater. And so we need a tool to use to be able to simulate what impacts it's going to have on our environment. And so groundwater models give us a way to do that. One thing I want to stress is that here at the district, modeling is a tool that we use, but it's not the only component of a hydrogeological assessment. So it's important at the onset of building a model, clearly defining what the purpose of the modeling effort is, and that will help determine what type and level of modeling is actually needed for the question you want to answer. So this flowchart, I know there's a lot of steps here, but it does capture the kind of protocol we go through in model development and actually running our models. So like I said, the first step is clearly defining the purpose of your model. And from there, you'll move on to building what we call a conceptual model that represents your understanding of the system. At this point, we'll begin assembling the data that we need for our model. I'll go into that in a little bit more detail in the next couple slides. And this will include like our aquifer properties as well as the stresses to our system. Then we move on to model grid design. So all of our models use like a rectilinear grid. And so in our grid, we have a set of rows and columns, and there's a number of decisions that need to be made, including like, what region of interest do you want for your model? That will determine, how the extent of your model, as well as your grid size. So depending on what you're using the model for, you may want to capture more detail in your model. So you may want to have a smaller grid size in that example. A model can only, calculate things within its grid size. So the coarser grids you have, you're not capturing as much detail as you would with a smaller grid. From there, we'll move on to defining some of our what we call boundary conditions in the model. So these are sources or sinks of water in our model. And then we move on to one of the most important steps in model development, which is model calibration. So model calibration is essentially a fine-tuning of the model that we do to improve the accuracy of our model in reproducing measured heads and flows. So I'll show you some examples of that in the next couple slides because it's a very important part of our procedure here. Then we move on to a step called model validation. This is an equally important step in the modeling process. And so validation is a way that we test that our calibrated model can reproduce results under a different set of stresses. So, for example, we may have calibrated our model to a specific period of time. We will then run the calibrated model under a different period of time, changing, for example, the pumping. And then we'll check to see that under that other period, is our model reasonably matching heads and flows from measured data. And from there, we'll move on to running the model and using it for model prediction purposes. One of the steps, I don't have it highlighted here, but typically for our models, especially those that are used to support our regional water supply planning efforts, those will go through a peer review process as well. So we'll have a team of technical experts as well as stakeholder input into the model, and our hydrologists and modelers here will work to incorporate those comments. And so this can be a back and forth process where we work with that team to finalize the model. Okay, so now kind of moving into model grid world. This is an example of a model grid that we have for our area of interest. And so we have a number of rows in our grid, we have a number of columns, and then we also have vertical layers in our grid. So these vertical layers represent our various aquifers and confining units that we're simulating in the model. And so for these different layers, there's a number of things we have to define, including, the thickness of the layer, the properties of the layer. This would be like storage, hydraulic conductivity. These are things that we need to define in our model. They can also be things that we calibrate the model for. So we may, have an initial estimate of what we think the hydraulic conductivity of an aquifer is, and then we may calibrate that within a reasonable range during the calibration process. Um, we also have groundwater pumping, which is obviously a major input into our groundwater models. We have a set of staff here at the district who work very hard to compile all of the groundwater pumping data that we need for our models. So this is from various use types, public supply, agricultural uses, landscape, recreational, all of that's compiled in a database by our staff, and they work very hard to put that data together. And they're working with other agencies and other water management districts in certain cases to put together that database. And that database is then used directly as input into our groundwater models. We also have, like I mentioned previously, we need to define our recharge rates into the model, as well as our evapotranspiration rates out of the model. And then we have some additional boundary conditions that have to be set in our model. So at our lateral boundaries, these are what we call the edges of our model. We need to define how we want to represent those in the model. Again, these can be places where water is coming in or out of the model, or in certain cases, there's no flow exchange happening at all here in these boundaries. So these are just additional inputs that we have to define in our model. And then we have surface water interactions. So even though I'm talking about groundwater modeling here, surface water is obviously a major part of our flow system. So there is interaction and exchange happening between groundwater and surface water. And so there are ways to semi-integrate that into our groundwater models using ModFlow. And so what you can see here in this image, we have lots of river systems, streams, we have springs represented here, and we have a number of lakes in our state, in our district. And so in ModFlow, you can represent these in the groundwater flow model. And like I mentioned, these are boundaries where you can have flow leaving or entering the groundwater flow system. And essentially what the model does is it calculates that rate of flow based on some inputs that you assign at each of these locations. Okay, so I wanted to just give a little bit more information on model calibration and show you guys some examples of what we look at during the calibration process. So like I mentioned, this is a procedure. I used the word fine tuning earlier where our model parameters, and these are mostly things like aquifer properties, are adjusted to reduce the error in our model. And when I talk about error, I'm talking about how the model values are matching our known data. So where we actually have measured heads and flows. These are called our calibration targets in the model. And for groundwater flow models, we're usually calibrating to measured groundwater levels. So in our monitoring well network, we have an extensive monitoring well network where we have measured groundwater levels. We have measured spring discharge that we're calibrating to. In certain cases, we can have estimates of base flow, so the groundwater contribution to our rivers and streams. And then we can also calibrate to things like lake seepage rates, so the exchange of water from our lakes into the groundwater flow system, or even lake stage. So at the onset of model calibration, what you need to define are your calibration metrics. And so this table is illustrating an example of that right here, where for our various observations in the model where we have measured data, our calibration targets, such as groundwater levels, lake levels, stream flow, we establish a statistic or metric that we use to basically assess if our model is meeting our criteria for what we call calibrated. And so in this example, if you were to look at groundwater levels, the statistic that we're using is mean absolute error, and we want our groundwater levels from the model to be within 5 feet of measured levels for all of our observed data. And so this is just an example of a metric we may use. But I also wanted to show you guys some examples of what we're looking at graphically or spatially when we do model calibration. So like this is showing here, we will look at the correlation between observed and modeled groundwater levels. So we want this to be a strong correlation here. As you can see in this example, it is. If we have a transient model, remember that transient is simulating changes through time. So in that case, we can actually see how the model is doing in terms of capturing the changes in levels through time due to seasonal variations and whatnot. So again, this would be an example of one that's doing a pretty good job of matching the observed data. We also look at the spatial distribution of our errors. So when I say errors, I'm talking about the differences between the modeled and measured values. So we'll often plot these up spatially. One of the reasons we do that is to see if there's bias in the model. So in this example, the red areas, the red dots you see, were underestimating levels, and in the blue dots we're overestimating levels. So we will look at this to make sure that there's not a specific area where we may be overly underestimating our groundwater levels. Okay, so I'd like to talk about some of the model applications and how we use groundwater flow models here at the district. So our groundwater flow models are used to support our district's core missions of preserving and protecting water supply and natural systems. So I'm going to focus on three areas where we use groundwater flow models. These include our permitting program, our minimum flows and levels program, as well as our regional water supply planning program. So groundwater flow models are used in permitting to evaluate impacts from consumptive use permits, so CUPs. So CUPs are basically allow reasonable beneficial uses of water, such as water supply or agricultural uses. However, it's the district's job to make the determination that these uses do not interfere with other legal users of the water or interfere with our environmental resources, so our lakes, our springs. We need to make sure that there's no significant harm done to those during the permitting review process. So during that review process, hydrologists are running groundwater flow models under whether it's a change to an existing permit or a new permit that comes in. They'll run the groundwater flow model with that additional pumping or removal of pumping in cases and look at the impacts on groundwater levels. Groundwater flow models are also used to support our minimum flows and levels, or MFLs program. So I know there was a webinar on MFLs recently, so I advise you to check that out. It was a great talk for more information about MFLs. But to broadly define it, they define the limit at which further water withdrawals would be significantly harmful to the water resources or ecology of an area. So to make those assessments, we'll often have to use groundwater flow models to understand if MFLs are being met for what we call a current pumping condition or future pumping conditions. So groundwater flow models can be used in this case in combination with surface water models to make that assessment. So we'll typically use a groundwater flow model to look at what's the impact of pumping on a system. That information will then be fed into surface water models that are used to assess the MFL for current pumping, as well as a future projection of pumping. When that assessment is made, the questions that are being answered are the MFLs being met under our current water demands? If the answer is no, then a recovery strategy will need to be developed for that system. If the answer is yes, but then they're not being met under future water demands, then a prevention strategy will be developed for that system. In both these cases, groundwater flow models can be used to support the development of these strategies for these systems. And the last one I wanted to touch on was how groundwater flow models are used to support the development of our regional water supply plans. So these are, per the Florida statutes, we develop these water supply plans to identify future water supply needs for a 20-year planning horizon. So these are approximately updated every 5 years, and you can visit our webpage here for more information on that. But our three planning areas we have here are the North Florida, Central Springs, East Coast, as well as Central Florida. And so groundwater flow models are used to, identify for a, projected future use of water, what impacts are we going to see on our water bodies. And basically it's a balance between, the water needed by people and the water needed by the environment. So groundwater flow models are used to make those assessments and, even test alternative water supply projects. So in that case, a solution may be to have a recharge project or have an aquifer storage recovery project. And so groundwater flow models can be used to assess the impacts of those projects for developing alternative water supply. So this map here is showing you some of the groundwater flow models that we use at the district. The different boxes are representing the extent of these different groundwater flow models. So one thing I want to point out is you can see that they range in size greatly. So a lot of these depend on the specific purpose of the modeling effort, like I mentioned. So we have some what we call more local scale models, like our Keystone Heights and Palm Coast model. And then we have more regionally extensive models, like our NFSEG model, which is the largest blue box here. Another thing I wanted to point out, which I think I mentioned this earlier, but you can see that these models do not align with our water management district boundary, for example. So I wanted to emphasize that the modeling process is a joint effort. It's an interagency effort in most cases. So we're working with the other water management districts to assemble the data and perform the modeling, and we're working with other agencies and stakeholders as well. And so if you visit some of the links I provided before, you'll see where you can access some of these files on our website. But of course, if you have any questions about any of these specific models, you can contact us directly here at the district. And lastly, I just wanted to share some additional resources. So if you visit our website and our data groundwater page, you'll come to this page right here. So there are some available groundwater resources for you if you'd like to get more information about our groundwater flow models. There's also some GIS data available at this site. And there's also what we call the hydrogeologic information system. So this is a great database you can access if you want to get some data related to groundwater, such as borehole data or lithologic data. So there's all kinds of data on here. So I encourage you, if you want to see some of this data that we're using for our models, you can visit this system right here. And with that, I'll conclude and we can take any questions anybody has.
Thank you so much, Lainey, for that great overview of groundwater modeling. It really helps to show how that data gets utilized that the district collects, and all the districts and the other agencies. It was really a fabulous presentation, and I know I learned a whole lot. One of the things that you did mention was some of the uncertainty that you have within models. And so I was curious, can you address how you address that uncertainty?
That's a great question. So uncertainty that's inherent in our models. So there's uncertainty associated with the data itself. There's uncertainty also associated with, our parameter values in the model. So like I mentioned that you alluded to before, we don't have data everywhere. So places where we don't have data, we're often making interpolations between those data points. So uncertainty analysis is a process that we do incorporate here into our modeling. And an example of how we'll address uncertainty is, like I mentioned, during calibration, we'll come up with a final set of values for our model, our parameter values. And there is a realization that there could be multiple combinations of those values that still produce a calibrated model. And so one way that we've looked into uncertainty is we'll basically use some automated approaches to run various iterations of our model with different parameter values. And in certain cases, we could generate hundreds of different models that are still calibrated, as we call it, by our metrics. And then we'll use some statistical analyses to basically quantify what the uncertainty in our model is based on those ranges of models that we have now to be used for model prediction. So it can get quite complicated, but it is an important part of the modeling process, and it's something that we have and will keep incorporating into our model development through the future.
Wonderful. Well, thank you. There was a follow-up that kind of goes along with that model calibration of how often do you conduct model calibration, and is there a time that you say, or a specific length of time that it takes before you're like, all right, hooray, we are happy with this model. We know it's reliable.
Right.
So
So
are there different iterations?
yeah, so that's a good question. And it kind of depends, one, on the modeler. There are different approaches you can take to model calibration. So there's what we call a manual approach. And so this is where, the modeler is, manually going through and making adjustments to parameter values to improve the accuracy of the model. And then there's also been the development of automated approaches that help us do this in a quicker fashion. So these utilities basically do a lot of the work for us. There's still a lot of inputs that need to be defined by the modeler if you're using automated calibration, but there are different utilities that will go through the various iterations until we've reduced our error in the model. There's I won't get into too much of the technical details, but essentially we're trying to reduce what we call an objective function in calibration. And so once, once that's been minimized, the calibration is essentially finished. But I do want to note that an important part of calibration is that you're not just looking at the error in your model, but from the modeler perspective, you're also making sure that conceptually the model makes sense. So, you know, there's still a lot of work done after we may think that a model is calibrated. We will go back and review that, you know, based on the knowledge we have as hydrologists and geologists and the available data out there, we make sure that conceptually this makes sense. So we're making sure that our aquifer properties are within ranges that are reasonable based on data we do have. And so there's always, you know, there is a point where you have to say, okay, we've calibrated this model to the best of our ability, and we'll move on to the next stages, such as validation, where we actually validate that the model's able to reproduce measured data in a different setting.
Great, thank you so much.
Mhm.
We're going to take one more question, and I do promise that I will get back to all of you that entered questions. That it shows that there's a lot of interest in modeling and the ways that we're doing it at the district. And so that question is one about, in addition to that physical flow modeling, are there also chemical and solute transport models being run at the district?
Right. So that's a great question as well. So I didn't talk too much about that in this presentation, but most of the models that we run are modeling our freshwater system. Obviously, we have saltwater present at great depths in our aquifer, and we have saltwater intrusion happening, you know, on the coastline. So there are models and codes out there that allow you to simulate what we call variable density. So you're also modeling saltwater and freshwater in a single model. And so we have done some of that at the district in the past. We've also done some upconing analyses as well. So when you pump a well, there is a chance for upconing to occur where you're essentially pulling up saltwater due to the pumping, the actual physical process of pumping. And so that's something that we've looked into here. I touched on some of the applications of the model. So from the permitting side, there's also, you know, water quality investigations that are done from that side to make sure that things like water quality degradation through saltwater intrusion is not an issue through consumptive use permitting. So we are also involved in those efforts, working with the regulatory group to use models to answer those questions.
Well, thank you so much, Lainey, and thank you all for attending our presentation today. Get in any of those last questions that you might have, and we'll get a written answer to you back in your email. And again, Lainey, thank you so much. And
Sure.
please do join us for our next webinar on Springs projects. Have a great day, everyone, and happy Earth Day.